Section 6 of Chapter 23 deals with a phenomenon called back EMF. In Chapter 22, we talked about motors, devices where we took electrical energy, we ran it through a wire. The wire was sitting inside a magnetic field that creates a torque that causes it to rotate, and so we get mechanical energy out of that. In Chapter 23, we're talking about generators. Those are devices in which we have some mechanical process that's creating rotation. The thing that's rotating is attached to a loop of wire inside a magnetic field, and as that loop of wire rotates, the flux is changing, and so that creates an induced EMF that causes electricity to flow. So in a generator, we've got mechanical energy, mechanical process, creating electrical energy, electricity. Other than the input and outputs, whether we're doing mechanical and producing electrical or vice versa, these two devices are basically the same. There's a coil of wire inside a magnetic field, and that coil of wire is rotating. There are a lot of similarities here. So the question should come up, why doesn't Faraday's law apply to motors? Well, in fact, it does. Let's zoom in here and take a closer look at this. In the motor, we have a current flowing through the wire, goes up through the wire, up through the left side, across, and down through the right side. And because this wire is sitting in a magnetic field, that current experiences a force due to the magnetic field. F equals ILB sine theta. That loop then rotates. So as it spins around, then there are brushes which will break the connection with one wire and make contact with the other wire so that we always get torque in the same direction so that it continues to spin. But just before the brush breaks contact here with the one leg, the wire has current flowing in it, going up on one side, down on the other side. Now let's come back to Faraday's law. Let's ask the question, what is happening to the flux, and what does Faraday's law tell us about that flux? Well, in the picture on the left, I have zero flux. Magnetic field is going left to right, and the way the loop is oriented, there's no flux through the loop. Another way to say that is the normal to the area is at 90 degrees to the magnetic field. And so cosine of theta is 0 in that case, and there's no flux. As it rotates, though, it will add flux in this direction. So now there is flux in this direction. There's a magnetic field pointing through the loop of wire. So let's walk through the steps of Lenz's law, Faraday's law. So I've got a picture drawn. I have a magnetic field pointing into, or from left to right, through this loop of wire. It has gone from 0 to some non-zero value, so it has increased. It's increased in this direction, from left to right. Lenz's law tells me that the loop will oppose that change in flux, meaning it wants to create its own magnetic field pointing from right to left. To do that, if you go through the right-hand rule, to do that, it will need to create a current. It will need to create a current in this direction, which is opposite of the current that was flowing. As the motor spins, Faraday's law induces an EMF, induces a voltage, which opposes the current that's flowing through it, causing it to rotate. Let's go back to our normal view. So here is a circuit that describes that situation. In a motor, I have an EMF that they call a driving EMF. The idea is that this is what the motor is plugged into. The driving EMF is the 120 volts if it's plugged into the wall. This is what's causing the rotation. When I close the switch, current flows through the motor, which has some resistance because it's made out of wires. But as that motor rotates, there's a back EMF. There's a voltage opposing what I'm trying to do, or what this 120 volts is trying to do. And so it opposes, it's opposite of this orientation. as current flows through this circuit in this direction, the back EMF is going to try to oppose that. And that's why it's called a back EMF. Now, it has an arrow drawn through it in this picture because it's a variable voltage. And you can see that if we write down our EMF equation. So not only does it vary over time, but notice that it depends on the speed of rotation. So when omega is 0, meaning there's no rotation, so when the motor first starts, when we first plug it into the wall, there's no rotation, and so the EMF is 0. But eventually the motor starts turning, it speeds up, and it runs at some maximum value, what's called its operating speed. So this is at startup, and then we have at operating speed. The angular velocity is equal to some non-zero value, and so we have a peak EMF, induced EMF, that's equal to NAB omega, where omega naught is the operating speed, or related to the operating speed. So obviously it varies. That's why we have the arrow through the battery here. When we first turn on the motor, there's no rotation, so there's no back EMF. But as the motor begins rotating, it starts producing a back EMF. And as the motor gets faster, the back EMF increases. So let's take a look at an example problem. They tell us a motor, let's keep this picture here. A motor with an internal resistance of 2 ohms is powered by a 120 volt source. When running at its normal operating speed, it draws 10 amps of current. 2 questions. 1, what current does it draw at startup? And 2, what is its back EMF at operating speed? So let's draw a picture of each situation. Let's start off with at startup. So at startup, omega is 0, which means the back EMF is 0. And so my circuit would look like this. The resistance from the coil of wires, the back EMF, but it is 0 at startup, and then I have 120 volts. My resistance is 2 ohms, and the question is asking me what is the startup current. So let's call this I sub S for startup current. Well, this is just simply Ohm's law, or we could treat it as a Kirchhoff's loop rule. Start at one point, walk around the circuit. So I have 100, if I start at this point, I have 120 volts positive, because I'm going from negative to positive. As I walk around the circuit, I'm going with the current, so that's a drop of I times R. So that's the unknown I times the R. And then at startup, this is 0. It's initially not rotating, so there's no back EMF, so I'm back to my starting point. That equals 0. And so the startup current is just the 120 volts divided by the 2 ohm resistance is 60 amps. At operating speed, draw the circuit again, back EMF, which is variable, the driving EMF, which is 120 volts. This is the source that it's plugged into, 2 ohms, there's some current flowing. And they tell me that at operating speed, it draws 10 amps of current. So when I first turn it on, it draws 60 amps of current. This was the answer to part A. So when you first turn it on, it draws 60 amps of current. But as the motor speeds up and the back EMF grows, the current decreases. And so what we are looking for is what is the back EMF if we know that there's 10 amps of current flowing when the motor's running at its operating speed. So again, we're going to do a Kirchhoff's loop. We'll start at this point, walk around the loop. So I have a positive 120 volts as I walk across the battery. Then when I go across the resistor, I'm going downstream, so that's minus I times R. I is now known as 10 amps. R is 2 ohms. And now I have a back EMF, and that's what I'm looking for. I'm going from the positive side to the negative side, so I'm stepping down, so that's minus whatever that EMF is. and then I'm back to my starting point, so that adds up to 0. So then the EMF is just 120 volts minus 20 volts is 100 volt back EMF.